Hello my friends and welcome back to the You Can Do TV channel. The BAMTEC Dynamic Twin MMR is ready for deployment. This advanced machine brings unmatched flexibility to rebar processing, capable of handling epoxy-coated, galvanized, or fiberglass GFRP bars. Foundation Steel will use it to produce prefabricated, customized rebar carpets, processing sizes from number 3 to number 11 with precision. Bars up to number 6 are drawn directly from coil, boosting material efficiency and reducing waste. Unlike the welded model shown, this unit ties the bars, a key distinction that allows broader application and field adaptability. With this powerful addition, Foundation Steel is positioned to deliver faster, more efficient, and highly customized reinforcement solutions for the construction industry. BAMTEC Rollout reinforcement is not only revolutionizing slab construction, but is now also being applied effectively in vertical wall structures. These prefabricated reinforcement carpets are assembled off-site, then delivered, labeled, and rolled into position with remarkable speed and precision. Once on site, each unit is lifted and unrolled directly onto the wall formwork, significantly streamlining installation. Compared to traditional loose bar methods, this approach delivers up to 50% time savings and 60% reduction in labor demand. BAMTEC ensures consistent bar spacing, minimizes material waste, and enhances site safety. This method is ideal for high-efficiency construction projects demanding speed and accuracy. BAMTEC, redefining reinforcement one wall at a time. The West Side Place project, completed in 2022, stands as one of Melbourne's most significant high-rise developments. This time-lapse captures the multi-stage construction process from groundworks to final cladding. Work began with deep excavation and piling to form the building's substructure, followed by the formation of the reinforced concrete core. As towers rose floor by floor, climbing formwork systems enabled rapid vertical progress. Tower cranes operated continuously, lifting prefabricated rebar cages, formwork panels, and facade elements. Structural steel and concrete slabs were placed in a tight cycle of reinforcement, pouring, and curing. As the superstructure reached full height, facade installation began using curtain wall systems, while mechanical and electrical fit-outs progressed internally. By the final phase, finishing trades completed interiors across residential, hotel, and retail components. Landscaping and public realm works were added at ground level. This large-scale development showcases coordinated sequencing, efficient material handling, and advanced high-rise techniques, transforming Melbourne's skyline with precision and speed. At Quarter Mile in Edinburgh, the BAMTEC reinforcement system was deployed to accelerate slab construction. The bottom mat was rolled out first, followed by precise placement of the top mat, each custom fabricated off-site for maximum efficiency. Using BAMTEC's pre-assembled, flexible steel reinforcement mats, a total of 20.029 tons was installed in just one working day. This streamlined process significantly reduced manual handling, improved site safety, and ensured high placement accuracy. BAMTEC proves ideal for large slab areas, delivering time and cost savings while maintaining structural integrity on fast-paced urban construction sites like Quarter Mile. Rising over 300 meters into the Kuwaiti skyline, the Aema Tower forms the centerpiece of the Aema project, the largest commercial complex in Kuwait City. With more than 380,000 square meters of usable space, the project includes over 65 stories above ground and 3 basement levels, spanning a footprint of 90,000 square meters. The structure adopts Kobac's voided slab technology, significantly reducing material usage and structural dead load. Flat slabs, 40 centimeters thick, incorporate the SLM 260-280 module, resulting in over 35,000 square meters of slab area formed with Kobac's elements. This design enables a 20 centimeters increase in clear ceiling height per floor while reducing steel consumption by 25%. By integrating void formers, the project avoids using more than 9,370 tons of concrete and cuts carbon dioxide emissions by approximately 780 tons. The lighter structural loads also translate into smaller column dimensions and optimized foundation systems. At the heart of modern precast construction, Keegan Precast's facility in County Meath showcases an advanced integration of automation and engineering expertise. The process begins in the drawing office, where in-house engineers and draftsmen use tailored CAD/CAM software to develop detailed 3D models of each precast twin wall and filigree floor slab. These models include reinforcement layouts, embedded items, and cast-in components. Once approved, digital files are transmitted directly to the carousel system. Each steel pallet is plotted with exact shapes, cutouts, and void locations. Magnetic shutters are cleaned and placed along the plotted outlines. Cast-in items like electrical boxes are fixed to the pallet, sealed with release oil to ensure edge quality. Next, reinforcement cover spacers are installed, and steel is automatically drawn, cut, bent, and positioned by a robotic system as per the model. LC connectors, insulation, and wall ties are added, ensuring correct geometry and spacing. Concrete is mixed on-site using in-house aggregates and poured with uniform compaction via an oscillating pallet platform. After curing the first skin, it's inverted and joined with the freshly poured second skin. The composite panel is then cured again, demolded, and moved using a tilting table to prevent damage. Finished panels are loaded onto custom transport stillages, ready for site installation. This system ensures structural integrity, reduced labor, and faster build times. Blocking noise from highways, rail lines, and industrial zones, providing essential noise control for growing communities. Precast concrete sound walls are more than barriers. They're engineered solutions that rise quickly, perform reliably, and stand the test of time. Let's explore how these walls are manufactured, transported, and installed with precision from start to finish. These walls are manufactured off-site in controlled conditions, ensuring consistent quality and structural reliability. The process begins with pre-pour operations, including preparing steel forms, installing reinforcement cages, and placing embedded components such as lifting anchors or connection hardware. Every detail is aligned to design specifications. During casting, concrete is poured into the molds and consolidated through mechanical vibration to eliminate voids and ensure strength. Surface finishing is applied to meet project-specific aesthetic or textural requirements. Panels are then left to cure under regulated conditions. Following this, post-pour operations involve form removal, detailed inspections, and minor surface corrections. Finished panels are transferred to a storage area, where they remain until ready for shipment. On-site, panels are installed using cranes, with careful placement and alignment onto foundations or columns. Joint treatment and any final finishing works are completed to ensure seamless integration. By prefabricating sound walls off-site, construction time is reduced, site disturbance minimized, and long-term performance assured, making precast concrete sound walls a sound investment in urban infrastructure. The Huntington Apartments project has successfully reached structural topping out in both towers, an engineering milestone reflecting months of precise planning and execution. Each building features a reinforced concrete frame system, with vertical load-bearing elements constructed using high-efficiency Jumpform methods. The floor plates consist of post-tension slabs, selected for their ability to span longer distances with reduced thickness. This approach not only optimizes concrete volume, but also lowers dead load, allowing a leaner structural design. Both buildings progressed in parallel, with synchronized construction cycles to streamline equipment use and manpower allocation. Coordination of crane operations and concrete pours was critical across the twin structures, especially during simultaneous slab pours. Core walls were advanced ahead of the main decks using climbing formwork, maintaining structural stability and scheduling efficiency. With the primary structure complete, the project now transitions to envelope and services installation, backed by the precision of its structural execution. At the heart of central London, the new eye hospital project, Project Oriel, is pushing construction efficiency with BAMTEC Rollout reinforcement technology. From 10 mm to 32 mm bar diameters. Once delivered, the BAMTEC mats are craned into position. Each roll is secured with tags, which are cut on site before the carpet is simply unrolled across the deck. Minimal tying is required, only at the ends to prevent movement. This significantly reduces labor time compared to traditional loose bar fixing. In column zones, positional couplers are used. After all mats are in place, cranked bars are connected to the coupler system to maintain continuity and integrate punching shear reinforcement. This eliminates the need to tie these bars separately later. The bubble deck system is an advanced biaxial hollow-core precast slab solution that eliminates unnecessary dead weight. By strategically placing recycled plastic spheres within the slab, the system reduces concrete volume without compromising structural performance. This engineered voiding technique lightens the slab and enables span lengths up to 50% longer than conventional solid slabs. Ideal for multi-story buildings, bubble deck enhances sustainability, reduces material usage, and accelerates installation, streamlining both structural efficiency and construction timelines. The Berkel precast basement system begins with a design phase supported by integrated computer modeling. Each element of the basement, walls, slabs, and connections, is planned to millimeter accuracy. Using advanced CAD systems, the design is optimized from the outset, integrating all components digita. In the factory, concrete components are cast under controlled conditions. Reinforcement is pre-arranged based on structural load requirements, and all openings for utility connections are included during fabrication. Once cured, elements are transported to site with minimal on-site modification required. Once on-site, the process moves fast. A specialized Berkel installation team prepares the foundation bed with exact tolerances. Using heavy lifting equipment, each precast panel is placed in sequence. Walls first, then floor and ceiling slabs, ensuring structural stability and perfect fit. During assembly, positional connections and integrated ceiling systems are installed to make the basement 100% watertight. The CLIMATEQ system can be applied where enhanced insulation or moisture control is required. Final checks include alignment verification and water sealing inspection. Within days, your basement is complete, fully load-bearing, moisture-resistant, and guaranteed for 10 years. The use of precast elements significantly reduces on-site construction time while maintaining quality. This method is particularly suited for residential and light commercial basements, where consistency, speed, and performance are priorities. The Bellside Bridge, one of Scotland's most frequently struck railway bridges, was successfully replaced using an advanced, precision-driven process. The project began with site preparation at the former Cleland station, where a dedicated crane platform, access road, and assembly area were constructed. Just 5 miles from the site, precast concrete components, including 2 hollow bridge deck units and 2 edge slabs, were manufactured, weighing a combined total of 260 tons. This proximity minimized transportation time and reduced logistical complexity. A major innovation was the use of self-propelled modular transporters, SPMTs, which transported the fully assembled bridge deck to site. The deck was then rotated and aligned using a hydraulic turntable system, marking the first use of this method in a UK rail application. A 650-ton crawler crane was used to lift and precisely place the massive deck elements. Following the installation, works continued with deck surfacing, joint sealing, and reinstallation of the track and overhead line equipment. The bridge clearance was raised to 5.2 meters, effectively reducing the risk of future strikes. All activities were executed within a 54-hour railway possession window. The success of this project is a testament to meticulous planning, the advantages of off-site precast fabrication, and the use of modern transport and lifting technologies. Bellside Bridge now stands as a benchmark for future infrastructure upgrades across the UK rail network. The Smart 13 BAR is a single-direction automatic stirrup bender designed to process steel bars up to E13mm, number 4. Equipped with a barcode reader, it allows quick loading of processing programs. The flat working surface ensures easier production of coplanar elements. With a high pulling speed of up to 110 meters per minute, it supports fast and efficient operation. Pre-arranged bending pin positions adapt to different bar diameters, while bar usage control helps optimize material efficiency. Powered by digital electric servo motors, the unit offers precision and reliability. Compact and mobile, it is easily transported to various job site locations. The Rebar Shearline 500 Pocket by Schnell Spa is a fully integrated, high-performance plant designed to cut, optimize, stock, and handle rebar efficiently for mass production. At the heart of the system is the CGS 500 hydraulic guillotine shear, mounted on a mobile frame, featuring a 500mm, 20 inches blade. This robust shear is capable of cutting 2 bars of 50mm or up to 80 bars of 10mm in a single operation. The process begins with the MEGAGENIUS automatic loader, which feeds the bars into the VA entry conveyor. This conveyor aligns and moves the bars precisely toward the shear. Once cut, the bars are transferred onto the VMT measuring and transfer track, equipped with ledges on both sides for left and right unloading. The VMT is separated from the unloading section, allowing both to operate independently for enhanced productivity. The cut bars are then received by the VS unloading track and sorted into the pocket optimizing storage pockets. These pockets ensure organized, efficient handling of different bar lengths. Additional components such as the RK storage rack, VRP distribution track, and ALC chain feeder facilitate streamlined material flow. The entire operation is driven by the RoboMaster 60 servo system, enabling precise control, high-speed cycles, and fully synchronized automation. The Brisbane Sky Tower, reaching 270 meters with 90 stories, is one of Australia's tallest residential towers. By May 2018, construction was rapidly advancing above ground, captured in this striking time-lapse sequence. At this stage, the Jumpform system was the centerpiece of vertical progress. This automated formwork allows the central concrete core, housing elevators and service shafts, to climb steadily, typically completing one level every 4 to 6 days. Hydraulic lifts raise the system after each pour, streamlining the process and improving safety. Around the core, the floor slabs were constructed using post-tensioned concrete. This method reduces slab thickness and material use while allowing for longer spans, ideal for high-rise towers. Rebar placement, formwork setting, and concrete pouring were coordinated in cycles, with workers often pouring one full floor plate per week. 2 high-capacity hammerhead cranes, each capable of lifting over 20 tons, serviced the site, delivering steel, precast facade units, and equipment to precise locations. Concrete boom pumps, reaching up to 50 meters, supplied fresh concrete directly to working levels. Facade installation moved in parallel. Glazed curtain wall panels, featuring low-E coated glass for thermal efficiency, were craned into place. These units were pre-assembled to speed up enclosure and allow internal fit-outs to begin within weeks. Inside, MEP, mechanical, electrical, and plumbing systems followed structural completion by just a few floors. Prefabricated riser modules and bathroom pods accelerated installation. By May 2018, over 50 levels had been completed, with workforce numbers peaking above 800 personnel on site daily. Sky Tower's rapid vertical rise was a result of tight scheduling, modular coordination, and advanced formwork technologies. The Brisbane Sky Tower was completed in 2019. Construction started in 2012, and the tower is now the tallest residential building in Australia. This build exemplifies the efficiency and engineering excellence required to construct a super-tall residential tower in a dense, urban center. In this time-lapse sequence, we follow the rapid and precise construction of a Glathar basement in Gros Corral. From the first pour to final detailing, each step is executed with engineered precision, laying the foundation for a durable, watertight, and energy-efficient structure. The process begins with the concreting of the base slab. Reinforcement is laid, followed by high-quality concrete placement. The slab is then leveled and compacted to form a durable and even foundation surface. Once the slab has cured, precast basement wall panels are delivered to the site and lifted into place by crane. These panels are pre-insulated, precisely dimensioned, and fitted together quickly, minimizing on-site labor and installation time. After positioning, the wall connections are concreted, ensuring structural continuity and water resistance. All joints, gaps, and connections are sealed to achieve a monolithic and watertight structure. Next, thermal insulation is applied around the basement walls. This helps regulate internal temperatures, enhances energy efficiency, and protects the structure from soil moisture. The final stage includes finishing works, such as sealing edges, installing drainage systems, backfilling the excavation, and leveling the surrounding terrain. Thanks to detailed planning and prefabrication, the Glathar basement can be completed within days, providing a solid, insulated foundation ready for above-ground construction. Precast staircase erection begins with precise surveying and preparation of the landing points. Once the crane is in position, each precast flight is lifted, aligned, and carefully guided into place by the crew. Temporary supports ensure safety and stability as stairs are grouted and secured to the structure. This method saves time, ensures quality control, and minimizes on-site labor. Within hours, a complete stair system is ready for use, accelerating vertical access during construction. At Granted Park in Cambridge, the BAMTEC Rollout reinforcement system was implemented with advanced positional coupler technology, pushing the limits of prefabricated reinforcement. The process begins with laying trick-track spacers beneath the B1 layer in the standard configuration. The B1 carpet mat is then smoothly rolled out, passing seamlessly over the columns where positional couplers have been precisely cast in. Once the bottom layer is in place, the B2 layer is deployed perpendicularly, forming the robust reinforcement grid. At each column, the central collar of the positional coupler is accurately aligned onto the embedded male half, already cast into the concrete. Cranked vertical bars, pre-fitted with the second male half of the coupler, are then installed to complete the vertical continuity. Following this, prefabricated U-bar perimeter details are positioned between the bottom and top reinforcement mats, ensuring structural cohesion. Heavy-duty wire chairs are added to support the upper reinforcement layers. Finally, the top BAMTEC carpet is rolled into place, interlocking precisely with cranked column bars to complete the system. The result is a faster, safer, and more efficient reinforcement solution, minimizing labor while maximizing structural precision. BAMTEC by Hi-10, engineering smarter, building faster. This time-lapse captures the full construction process of the City Center Casino in Las Vegas, one of the largest private developments in U.S. history. From excavation to topping out, watch how thousands of tons of steel and concrete come together with precision. Tower cranes swing into action. Prefabricated elements slot into place, and floor after floor rises against the desert skyline. This massive build showcases the scale, speed, and coordination required to bring a world-class casino resort to life in the heart of the Las Vegas Strip. Installing underground cables in the national grid involves several precise steps. First, the route is planned, approved, and surveyed. Once permissions are secured, the land is cleared, and a trench, typically 2.5 to 5 meters wide, is excavated. A thermal sand layer is added to help dissipate heat. Cables are delivered on large drums and unrolled in both directions. At least 6 parallel cables are needed for a standard transmission line. Before backfilling, expert technicians perform splicing in controlled environments, like tents or containers. After jointing, another layer of thermal sand is added. Then the trench is backfilled. A warning mesh is placed above the cables to prevent accidental damage. Farming is allowed on the surface, but trees and buildings are restricted. In February 2014, a complete turnout replacement and track renewal took place at the eastern entrance of Tochenl station. The project began with the removal of the old ballast and disassembly of existing track and turnout components. Heavy machinery, including rail cranes and excavators, was deployed to lift and transport old sleepers and rails. Once the substructure was cleared and graded, new ballast was laid to form a stable foundation. Pre-assembled turnouts were then carefully positioned using rail cranes. Precision alignment followed, ensuring the exact geometry of the new track. After placement, the turnouts and tracks were secured and tamped to stabilize the ballast bed. Final welding and connection of the rail joints completed the installation. With signal systems and control equipment reconnected, the track section was ready for reopening. This upgrade improved reliability and safety for traffic entering Tochenl from the east. VBMS cable-laying vessels are engineered for advanced offshore operations, featuring dynamic positioning 2 DP2 systems and 7-point mooring for stability. Their modular deck layout enables operation in both shallow waters and deep-sea environments. Each vessel is equipped with a 5,000-ton capacity turntable, which rotates to feed cable into the water via a precision-controlled tensioner. This ensures smooth deployment during inter-array cable installation between offshore wind turbine monopiles. The process begins with a first-end pull-in at the initial monopile. The vessel then lays cable along a pre-engineered route to the second monopile, where the cable is cut and guided through a cable protection system, CPS, before the second end pull-in. A quadrant system prevents cable overbending during final placement. For export cables, which connect offshore wind farms to the onshore grid, the vessel uses a plow system to simultaneously lay and bury cables. A winch pulls the plow ashore, followed by the cable. In shallow or nearshore zones, the vessel can beach to facilitate shore landing. If required by soil type, jetting tools like the transformer use high-pressure water to trench the seabed for precise cable burial. Wilco Precast's construction process emphasizes technical precision and efficient assembly. It starts with architectural drawings, which are translated into detailed shop plans by the in-house drafting team. Skilled workers prepare the molds, bend reinforcement steel, and pour concrete, strictly following quality assurance protocols. One of the company's standout innovations is Lightrete, a lightweight precast concrete that replaces traditional stone aggregate with pumice. This change reduces weight by approximately 50% while improving insulation and acoustic performance. Lightrete panels meet building code requirements without needing extra wall linings and provide superior fire and moisture resistance. Once panels are cast and cured, they are painted and pre-fitted with joinery before transport. On site, panels are lifted by crane and placed over precast starter bars in the floor slab, then secured with grout and temporary props. Welded plates provide final structural stability. The mid-floor and roof components are also prefabricated and craned into position, allowing an entire home to be assembled in just 2 days. This streamlined process showcases the technical strength and practical benefits of systems. Parkhouse, Oxford Street is a landmark mixed-use development situated in the heart of London's busiest retail district. Built on a constrained and complex urban site, the construction process began with deep excavation and ground stabilization to form the basement levels and prepare a foundation for the 6,000 square meter superstructure. Due to the proximity of adjacent buildings, contiguous piled retaining walls and ground anchors were used to prevent ground movement and ensure structural integrity during excavation. Once the basement and foundations were completed, the primary steel frame was erected to support the building's uniquely curved facade. The 9-story curved glass facade, based on cross-sectional toroids, is a major engineering feat. Over 800 individually shaped glass panels were designed and manufactured to accommodate the non-uniform curvature of the facade and roof. 624 panels were cold bent on site, while 214 panels at the sharply curved north and south ends were hot formed in a factory by Sunglass. Installation required a precise sequencing process, with tolerances limited to plus or minus 0.5 millimeters, as any deviation could have compromised the fit of the entire envelope. The building was completed with high-performance solar-controlled glass, integrated shading systems, and achieved a BREEAM Very Good rating. Sculptural glass spandrels by artist Walter Bailey, digitally transferred and kiln-fused into the facade, provide a unique artistic identity to this complex and ambitious architectural achievement. This is a complete transformation of Route 8, a major transportation corridor in Traverse City, Michigan. Team began underground, installing nearly 2,000 feet of new 24-inch water main. Along the way, they unearthed century-old steel-banded wooden water pipes, a rare historic find. Massive 6-foot-long water valves, requiring 240 turns to open, were installed horizontally to maintain clearance, a significant departure from standard upright installations. Simultaneously, over 2,300 feet of storm sewer and 2,100 feet of sanitary sewer were replaced. Curbs and gutters were poured, and more than 3,300 tons of asphalt were laid. Nearly 50,000 square feet of decorative sidewalk were placed, complete with ADA-compliant crossings and widened pedestrian paths. Once paving was complete, the team installed over 14,000 feet of pavement markings, including lane dividers, bike lane symbols, crosswalks, and directional arrows. These road markings were applied using high-visibility thermoplastic and paint, enhancing safety and organization for all users, drivers, cyclists, and pedestrians alike. Designed for multimodal use, the corridor now features protected bike lanes behind the curb, integrated bus bump outs, irrigation systems, and 45 newly planted trees. Motion-sensing LED street lighting was added for safety and energy efficiency. Through close coordination with property owners and utility providers, above-ground power lines were buried, and infrastructure was carefully threaded around existing features. Though the original deadline was November, the street reopened to traffic by late September, a full month ahead of schedule, about 105 working days, May 6th to September 26th. This project exemplifies what's possible with smart planning, technical precision, and a community-first approach. This is the full transformation of South Airport Road, a full-depth reconstruction project, captured from start to finish. The process began with the removal of existing curbs and milling of the old asphalt surface, followed by the excavation and adjustment of road grade to prepare for a new structure. Next, a curb machine poured fresh concrete curbs, while crews shaped the final grade and restored surrounding areas. With the groundwork set, the first base layer of asphalt was paved, and traffic was shifted to allow work to continue safely in the next phase. Crews repeated the sequence on the opposite side, removing old curbs, milling asphalt, and rebuilding the aggregate base. New concrete curbs were formed, followed by final grading and restoration. The base layer of asphalt was placed once again, paving the way for the final stage. Finally, a smooth top layer of asphalt was applied across the full corridor, creating a clean, durable finish. After a final traffic shift and surface checks, the South Airport Road reconstruction was completed, a safer, smoother, and longer-lasting route for the community. Welcome to Messick, Michigan, where Team Elmers took on the challenge of transforming the busy intersection at M115 and M37 into a modern roundabout, improving both safety and traffic flow. The project began with site clearing and traffic control, ensuring crews could work efficiently while keeping motorists safe. Excavation and grading followed, as old pavement was removed and the subgrade was carefully shaped to match the roundabout's geometry. Next, the team installed stormwater structures and underground utilities, preparing the site for long-term durability. With the base stabilized, crews moved on to forming and pouring curbs and concrete islands, shaping the circular layout of the new intersection. Once cured, the surface was paved with layers of hot mix asphalt, ensuring a smooth and reliable ride for all road users. Pavement markings and signage were added, guiding drivers clearly through the new configuration, while landscaping and restoration work helped blend the roundabout into the community. Despite rural conditions and tight timelines, the Elmers team delivered the project with efficiency and precision. The result? A safer, more efficient intersection that's built to serve Messick for decades to come. The construction of 4 Wellington Place in Leeds showcases a modern approach to urban development, completed from groundbreaking in 2018 to practical completion in 2020. As the 9th building within the Wellington Place master plan, it marked a significant milestone, the completion of the east end of this transformative mixed-use development. The process began with extensive site preparation, including earthworks, foundation piling, and concrete substructure works. Precision and sequencing were critical during these early stages to ensure stability and integration with existing infrastructure. Steel frame erection followed, forming the building's structural skeleton. Prefabricated elements were delivered and assembled on site, reducing construction time and improving accuracy. Floor slabs were cast progressively, and facade installation began soon after, comprising curtain walling systems with high-performance glazing to meet energy and acoustic standards. Internally, mechanical and electrical services were installed in coordination with floor-by-floor fit-out activities. Raised floors, suspended ceilings, and energy-efficient lighting systems were integrated into the design, prioritizing flexibility for tenants. Sustainability was a core focus throughout construction, with materials chosen for durability and low environmental impact. The project achieved a BREEAM Excellent rating, reflecting its commitment to responsible building practices. By 2020, 4 Wellington Place stood as a completed, high-specification office building, symbolizing progress in Leeds' commercial landscape and contributing to the vibrant, connected Wellington Place community. The development of 7 and 8 Wellington Place stands as one of the most ambitious and large-scale commercial projects in Leeds. From the moment the first shovel hit the ground to the final brushstroke of paint, this landmark build exemplified precision, scale, and vision. The project kicked off with deep foundation works, including extensive piling to support the twin structures. Heavy machinery dominated the early phase, as excavation and below-ground works set the stage for the towering superstructures that would follow. As the steel frameworks began to rise, the skyline of Leeds started to transform. The twin buildings advanced in parallel, with floor plates rapidly constructed using poured concrete and prefabricated components. External facades of brick and glass were applied with careful coordination, achieving a modern, cohesive architectural identity. Mechanical, electrical, and plumbing MEP systems were installed with military precision, routed through risers and ceiling voids to serve the expansive office floor plates. High-efficiency HVAC and lighting systems were integrated for sustainability and tenant comfort. Interior fit-outs brought the spaces to life. Reception areas, collaboration zones, and breakout spaces were finished to a high standard, reflecting the future of workspace design. By the time the project reached completion, 7 and 8 Wellington Place had become a symbol of Leeds' commercial resurgence, a statement of scale, quality, and urban regeneration. In modern precast production, automation is key to efficiency and precision. The SmartSet shuttering robot by Roundabout exemplifies this advancement. Designed for use in highly automated circulation systems, the SmartSet robot handles the fully automatic positioning, aligning, and fixing of shuttering elements onto steel pallets. Using CAD-based input data, the robot reads the layout and places shutters with millimeter accuracy. Magnetic formwork components are picked and placed by the robot's gripper arm, which adapts dynamically to various shapes and sizes. Integrated laser scanning ensures correct positioning while reducing the need for manual adjustments. The SmartSet robot also handles demolding. After curing, it identifies and removes shutters, preparing the pallet for the next cycle. This not only reduces labor, but increases overall production speed and safety. Highly reliable and customizable, the SmartSet system is a core element in smart factories, boosting productivity while maintaining precision and repeatability in every concrete panel produced. It is particularly effective in producing walls, slabs, and facade elements within tight tolerance requirements. Prototype testing of lead rubber bearing (LRB) seismic isolators evaluates performance under extreme conditions. Vertical loads reached 30,000 kilonewtons static and 15,000 kilonewtons dynamic, with up to 750 millimeters displacement. Horizontal capacity measured 3,000 kilonewtons static and 2,000 kilonewtons dynamic. Testing confirmed functionality at 1.5 meters per second velocity across a 20 meters travel path. What if you could build a high-quality, energy-efficient house in just 6 days? Not just a shell, but a fully functional, move-in-ready home. That's exactly what was accomplished using innovative foam concrete technology, a lightweight, insulating, and eco-friendly construction material that's transforming the way we build. Let's walk through the construction timeline. Day 1 begins with site preparation and construction of the foundation. Excavation is completed, the formwork for the base is laid out, and concrete is poured to create a solid foundation for the house. At the same time, underground utilities, sewerage and water supply systems are installed. By the end of Day 1, the groundwork is not just ready but completely functional. On Day 2, workers apply a waterproofing coating to protect the foundation from future moisture intrusion. Formwork is erected for the building's walls, setting the stage for the vertical structure. Crucially, the complete infrastructure ducting, including electricity, water, and sewerage, is routed through the formwork. This step ensures the home is smartly wired and plumbed before the concrete is even poured. Day 3 is when the magic of foam concrete really happens. Walls and part of the slab are poured with foam concrete, a unique mix of cement, water, and preformed foam. This process is fast, clean, and efficient. Sample sections are taken for quality assurance. Thanks to the lightweight and self-leveling properties of foam concrete, the structure begins to take shape quickly, with minimal labor and equipment required. Day 4 begins with the removal of the formwork, revealing smooth, solid walls. Additional slab sections are cast directly on the structure. Formwork is again erected, this time for remaining portions of the floor, and foam concrete is poured once more. All of this happens without delay, thanks to the fast curing and workable nature of foam concrete. By day 5, the focus shifts to interior and exterior finishes. Doors and windows, also known as joinery, are installed. The home's facade is completed, providing weather protection and visual appeal. Inside, tiling work begins in kitchens, bathrooms, and other areas, giving the interior its final touches. On day 6, the home enters the final stage. Painting work begins both inside and out. The sanitary ware, toilets, sinks, faucets, and kitchen elements are installed. Trimmings and interior boardings are completed, and a final layer of waterproofing is applied in sensitive areas. By the end of the 6th day, the home is 100% complete and ready for move-in. So why foam concrete? It's lightweight, reducing the cost of foundations, steel reinforcement, labor, and transport. It provides excellent thermal and acoustic insulation, 3 times more than traditional bricks, and requires no additional insulation. It cuts heating and cooling costs by up to 40%. It's fire-resistant, holding strong for 5 to 7 hours in extreme heat, and it's eco-friendly, producing minimal waste and emissions. This is the future of housing. Fast, affordable, sustainable. Foam concrete doesn't just build homes, it builds possibilities.